invite, and I apologize, Isthar Sofia, okay? She is a PhD student, okay, at the Federal University of Catalão. She has a master's degree in chemistry, and she has a mining engineering degree from the same university, okay? Thank you very much. Please join us here on the stage. Good morning to all of you. My name is Isthar. I'm a mining engineering, and I am a PhD student, and I study mining in my graduate work. I'm going to talk about the apatite concentrate, okay, from Catalão. There are several industrial processes that can be used in the manufacturing of phosphoric acid. We have the thermal treatment, okay, that consumes a lot of energy, but it is capable of getting a phosphoric acid that is highly pure. And we also have the wet process, okay, that is a more economic way of producing the phosphoric acid. And one of the production phases of the phosphoric acid is the acidulation and the wet process. And we also have apatite with sulfuric acid, with chloridic acid, with nitric acid, okay? And this process could be simple as the equations and the reactions presented in the previous slide. They are simplified, but it becomes a little more complex, not only because of the type of process, but also because of the mineral variability, the high mineral variability of the raw materials, okay? And we know that these ores, they have a high mineral variability. And there is a huge variation even inside the same mine. And if we compare the other ones close there in the Alto do Paranaíba, we're going to see that this variability is even higher, okay? And all of this contributes to take these impurities into the phosphoric acid. Some of them are more soluble, like the ions of aluminum, iron, and also sulfuric, the sulfates, the sodium, the potassium, and the ones that we don't want, thorium, uranium. And to adjust this phosphoric acid to the quality standards, we can add purification phases into the process. And now the extraction via solvents is the one most used by the industry to purify the phosphoric acid. And we have the patents, Ron Pulake, and it allows us to recover the byproducts, okay? And Prion, that uses a mixture of the organic solvents, and ether, diesel, okay.
The goal of this work was to deliver tests of liquid station extraction to get rid of contaminants and phosphoric acids produced by the apatite concentrate of Catalão. We first did some sampling and the characterization of that sample. We sometimes call it coarse concentrate because of the granulometer being P80 of 142 microns. And this sample was subjected to a mass spectrometry to analyze the amount of rare earth elements such as uranium and thorium. And we also did X-ray fluorescence analysis in CMOC. In addition, we also prepared a thin slice with these grains in one of the samples to analyze with SEM. in the labs of CRTE in Goiânia. For the acidulation, after the characterization of the samples, we used a magnetic agitator with heat to keep it in 80 degrees Celsius, and we tested two kinds of acid, the sulfuric and the chloridic acids. This reaction took 120 minutes, and this acid solutions using phosphoric acid were evaluated in terms of P2O5 with the chemosciac method. The fluoride was analyzed with potentiometric techniques, and the calcium with the CMOC quality control labs. We also did an EDXRF to analyze other contaminants. After the acidulation, we did the liquid-liquid extraction. We also used the magnetic agitator, and we used this acid solution from the previous phase to have an aqueous extract, and the organic extract would be the solvent and the diluent. And the diluent was tributyl sulfate, and we tested two solvents, hexane and kerosene. The extractions was done by 20 minutes, and the aqueous was 2 to 1. And we analyzed the chlorides, and we have an important observation. None of these acid solutions were given pre-treatment. So we did not do the phosphate or fluoride removal, and we did not concentrate the P2O5 with evaporation. Now let's go to the results. In the characterization, the X-ray fluorescence results, we have a concentrate with around 36% of P2O5, and we analyzed the oxides of niobium, iron, silicon, and barium and magnesium. The iron and silica was above 1%, the others were below. And by ICP-MS, we analyzed the light rare earth element. We have 7,474.92 of rare earth elements, and we have uranium 181 and thorium 152 ppms. By the micrography, we were able to identify that the concentrate is composed mostly by apatite, which is what we expected, but we also have the interference of some minerals that are contaminants, such as barite, iron oxide, badolite, vermiculite, quartz, and others. So these are the source of impurities that reach our phosphoric acid. In acidulation, we noticed that there was a good solubilization through both routes, and the content of P2O5 in the sulfuric route, it was a bit higher than the chloride one, but we could see that it was more diluted. But for the calcium, we see the difference that the calcium ions are solubilized in the chloride route. So we have 3.59% of calcium, whereas in the sulfuric we have the precipitation of phosphogypsum. So in this of the sulfuric rock we have phosphogypsum, I think, is 0.5. The chloridic was 0.28. In addition to this quantitative analysis, we did a qualitative analysis with the EDXRF, and we identified that the sulfuric route has a higher amount of iron, given that the intensity of the lines of emission are very high and with the sulfuric liquor. And when we compare with the chloride, we have less iron, but we have much more calcium, as confirmed by the quantitative analysis previously. We also saw that it has an increasing amount of, I am sorry, I didn't get that. In the liquid-liquid extraction, we have the percentage of the extraction in each one of the assays. We put here the results of chloridic acid and sulfuric acid. Remember, we used two different results, diluents, so that's why we have two different results for each route. So for phosphorus, the phosphorus was better extracted by TBP in the phosphoric acid produced by the chloride route. 36 to 38% of extraction we were able to achieve, whereas the liquors of the sulfuric we had 9 to 8. And the fluoride was extracted at the same time. In the chloride route, I have a better efficiency of extraction, 44 and 45, and the sulfuric route, we have 20 to 18%. We also did a qualitative analysis for this liquid extraction, and we noticed that the iron and the calcium were extracted in the phosphoric acid produced by the chloride route. This is not interesting. If my intention is to use the phosphoric acid in the organic phase to purify, I don't want to carry other impurities. So in this case, the chloridic liquors, the iron and the calcium were carried over. So what are the conclusions? First of all, for the chloride route, we see that we have a less waste, less residues, and the TBP was also efficient in the extraction of phosphoric acid with 36 to 38% of extraction. However, the selectivity was worsened once that we also carried over the ions of iron and calcium. And for the sulfuric route, although we had a lower percentage of extraction, we have a more selective extraction. We did not identify in qualitative analysis no other co-extraction. So it's interesting to analyze that route for future tests to increase performance and the stage of extractions with solvents to recover the phosphoric in the organic phase. When we analyze both routes, we see the use of diluents, and we saw that there was no difference. The extractions with hexane and kerosene, they were similar in all extraction tests, and the selectivity of TBP to the fluoride ions reinforces the need to the defluoridation process before or pre-treatment. So as we can see, as the fluoride was extracted by the TBP, it's competing in terms of selectivity with the phosphoric acid. So it's necessary to do this pre-treatment phase. I would like to thank the co-author, my friends Santiago and Camelia, and the advisors, Lincoln, Maya, and I would like to thank all the agencies for the government and the people who organized this wonderful event. I would like to end with a sentence from Isaac Asimov. We may be able to replace nuclear energy with coal or plastic by wood, but for phosphorus there is no replacement. This is a sentence from 1975. Today we can not say nuclear energy, we can say clean energy, but the idea is that if phosphorus cannot be replaced, we have to always try to work it out. So I am available for questions. Thank you. Thank you very much for your presentation. We do have time for questions. But it seems that everyone is shy today after the coffee break, but it was very interesting work, and it's so good to have our former students here presenting. Congratulations, and I wish you all the success in your research.